Welcome to Trinod Chemistry classes. In this video, I am going to discuss about chemical kinetics. This is my fifth video in chemical kinetics topic. In first video, I have discussed about what is kinetics, why we are studying kinetics. Then we have defined what is the rate of reaction. Based on this rate of reaction, we have classified the chemical reactions into three types: very slow reaction, and moderate reactions. Fast reactions. Very slow reactions, and fast reactions. The reactions whose rates are moderate or not very slow or not very fast, those reactions we are calling them as fast reactions, and we are studying the kinetics of fast reactions. And then we have we have seen how to determine rate of reaction experimentally. For that, we have plotted a reactant versus time or products versus time plot. Then we got a exponential there. We got a plot, and the slope of the tangent drawn to the plot, the slope of the tangent gives the rate of reaction. In my second video, I have discussed about factors affecting the rate of a reaction. There are 5 factors. One is nature of reactants and products. Second one is concentration. Third one is temperature. Fourth one is catalyst. And fifth one is pressure. In my third video, we have discussed about the effect of concentration in detail. For that, in that, I have discussed about the law of mass action, and then based on that, we have seen what is the rate equation or rate expression, rate constant. Then from that, we have brought the idea of order of a reaction and the molecularity of a reaction, and we have seen the differences between order and molecularity. Afterwards, I have defined half-life of a reaction. What is the half-life of a reaction? In my fourth video, I have discussed about zero-order reactions. First, we have seen what are zero-order reactions. Zero-order reactions are the reactions for which the order is zero, or the reactions for which the sum of the powers of the concentration terms is zero. Those reactions we called them as zero-order reactions. For zero-order reactions, we have derived rate constant expression for zero-order reaction. We have derived rate constant expression, and then we have derived an expression for half-life of a zero-order reaction. In this video, I am going to continue these zero-order reactions. Then I will move to first-order reactions. In my fourth video, we have derived an expression for the rate constant of a zero-order reaction. In that, we have assumed R gives rise to P, one reaction, a zero-order reaction, and then we have assumed that R0 is the initial concentration of reactants. R0 is the initial concentration of reactants, and R is the concentration of products, concentration of reactants after time t. Concentration of reactants after time t. Then we have derived an expression for half-life of a zero-order reaction, R0 by 2K, where T0 is the half-life of a zero-order reaction, K is the zero-order rate constant, J is the zero-order rate constant, and then R0 is the initial concentration of reactants. So from this expression, we can say that half-life of a zero-order reaction is directly proportional to concentration of reactants. That is initial concentration of reactants. Half-life is directly proportional to the initial concentration of reactants. If initial concentration increases, half-life increases. Then we need to discuss about some plots. Up to this, we have seen in the last video, and in this video, we need to discuss regarding some plots. For a zero order reaction, for a zero order reaction, from the definition, what we have seen, rate is equal to K into R naught power R power 0. R power 0 means 1. That is, rate is independent of the concentration of reactants. Whatever may be the concentration of reactant, rate remains constant. That's why the rate versus concentration of reactants plot appear like this. If plot is like this, then the reaction is a zero order reaction. This is one plot. Rate versus concentration of reactants. Rate versus concentration of reactant plot is like this. The rate is independent of the concentration of reactants. What that means, whatever may be the concentration of reactants, rate remains same. If you take 1 mole or 10 moles or 100 moles, for a zero order reaction, the rate is always same. It doesn't depend upon the concentration of reactants. Concentration of reactants. This is one plot. Now look at the second plot. If you see the second plot, we have seen K is equal to, what is an expression? R naught minus R by 2. I am rearranging the terms. I am slightly rearranging the terms. How? You see, here I am bringing T this side, R naught minus R. Now, if I bring this R this side and KT that side, it becomes minus KT plus R. Now I am writing it as a minus K into T plus R. Now, if you observe, it is in the form of Y is equal to mx plus C. Y is equal to mx plus C. Now, if I plot concentration of reactants versus time, concentration of reactants versus time. If I plot concentration of reactants versus time, then the plot is with like a straight line with a negative slope, with a linear equation with a negative slope, and the slope is corresponds to minus k, and the intercept curve gives the initial concentration of reactants. Intercept gives the initial concentration of reactants. This is the second plot regarding the zero order reaction. First one is rate versus concentration of reactants, which is parallel to the x-axis, whereas the concentration of reactant versus time plot is a straight line with a negative slope and an intercept, and the slope corresponds to the zero order minus of zero order rate constant. This is the second plot for zero order reactions. Now let us move to third plot. Just now we have seen half-life of a zero order reaction is, what is the expression? Half-life of a zero order reaction is E naught is equal to R naught by 2K. Now, if I write like this, 2K into R naught. Here, K is a constant, 2 is also constant. Then I am replacing with some other new constant, K dash into R naught. If I remove this K dash, then what will happen? P of is directly proportional to initial concentration of reactant. Now I am plotting like this. See, T of versus concentration of reactant. Now, which is in the form of, this equation is in the form of Y is equal to mx. Now that is passing through origin. Straight line passing through origin. So these are the three plots regarding this zero order reactions. Now we need to see what are the examples for zero order reactions. Maybe in an intermediate public examination point of view, they may ask examples. Give 2 examples for the zero order reactions, or give examples for the first order reactions. There are several examples are there. At least we need to remember the 2 examples. One is decomposition of heat.
decomposition of ammonia in the presence of catalyst. In the presence of catalyst, that is 2NH3 gives rise to what? 2NH3 gives rise to uh, platinum catalyst. Platinum catalyst N2 plus 3H2. So this is gas, this is also gas, this is also gas. Right? Decomposition of ammonia in the presence of platinum catalyst is an example for the zero order reactions. Now, the second example is decomposition of HI. Decomposition of HI on the surface of gold. On the surface of gold. That is 2HI gives rise to H2 gas plus I2 gas on the surface of gold. It is another example for the zero order reactions. Another example for the zero order reactions. Similarly, decomposition of nitrous oxide, N2O decomposition, N2 plus O2. It decomposes N2O nitrous oxide decomposes as 2N2O gives rise to 2N2 plus O2. This is also decomposition on the surface of metals, catalysts. This is also an example for the zero order reactions. So maybe with this we have completed the zero order reactions. Briefly, we have seen zero order reactions. We have defined what are zero order reactions. Then we have derived an expression for the rate constant of a zero order reaction. We have derived an expression for the half-life of a zero order reaction. Then we have seen some plots which are related to the zero order reactions. Then we have seen some examples for the zero order reactions. Examples for the zero order reactions. Now, in this class, I am going to discuss about first order reactions. First order reactions. What are first order reactions? The reactions whose order is 0, 1. The reactions whose order is 1. Whose order is 1 are called first order reactions. Are called first order reactions. The reactions whose order is 1. Whose order is 1 are called first order reactions. The reactions whose order is 1 are called first order reactions. The reactions whose order is 1 are called first order reactions. Here, let us consider, or we may define this definition. We can define also as the reactions. The reactions for which the sum of the sum of the powers of the concentration terms is 1. The reactions for which reactions in which the sum of the powers of the concentration terms is 1, then those reactions are also called as a order reaction. Simply we can say that the reactions for which order is 1 are called, whose order is 1 are called first order reactions. The reactions whose order is 1 are called first order reactions. First order reactions. Here, now let us consider a first order reaction. R gives rise to P. Let us consider one reaction. R gives rise to P is a first order reaction. R gives rise to P. Let us consider this is the one reaction. It is a, let us assume that it is a first order reaction. Here also assume that R not with the initial concentration of reactants. Initial concentration of reactants and R with the concentration of reactants after time. Reactants after time. Concentration of reactants after time. R not with the initial concentration of reactants. R with the concentration of reactants after time. Now, if I write rate expression for this one, what is the rate expression? Rate is equal to, as it is a first order, The sum of the powers of the concentration terms, as there is only one reactant, but the reactant power should be how much? 1, as it is a first order reaction. As it is a first order reaction, the power of the concentration term should be 1. Suppose if two reactants are there, whose sum is, here it may be 1, here it may be 2, it may be -1, then overall sum is +1. Or here with respect to A is 1, B is 0, then also order is 1 only. The sum of the powers of the concentration terms should be 1. Here, as there is only one reactant, now the rate equation is becoming rate is equal to K into R power 1. Then I can write it as a K into R. K into R. Now, see, we know that for this reaction, how we can write rate is equal to minus dr by dt minus dr by dt, which is equal to dp by dt, which is equal to dp by dt, which is equal to dp by dt. Now, if I substitute this, minus dr by dt is equal to, how I can write, k into r. Right now I need to derive, I need to complete this expression, I need to solve this expression to get the value for rate constant of a first order reaction. You see here K is called rate constant of a first order reaction. Suppose if I rearrange this term, dr by d is equal to K into d. On integration both sides, like in zero order reaction, if I integrate on both sides, then what will happen? See, integral minus dr by dt, sorry, dr by r, which is equal to integral k dt, as we need to keep some constant I. Previously in my fourth video I have discussed integral dx is how much? X plus constant I. Integral dx by x is ln x or ln x or log base e x plus I. Right? So this is the integral. Integration symbol is like this. This is corresponds to the integral. We'll read it as the integral. Integral dx by x is how much? Ln x plus I. Integral dx is x. You see, this expression was, this equation was used in zero order reactions, whereas now we are using this. Here dr by r. In place of x, what is there? Variable is here r. Right? Now I am writing it as the minus dr by r. Dr by r is equal to k into dt plus k into dt plus I. Now I can write it as the minus ln r is equal to k into t plus I. Let it be 1. Because as k is a constant, I have taken outside of the integral. So your k into integral dt plus I. So dx by x, that's why ln x. So this is the formula. Dx by x ln x is equal to integral dx is how much? X. That's why here, as it is a variable t, I am writing kt plus x. So in order to complete this equation, we need to find the value of I. We need to find the value of I. How to get I? So here, when t is equal to 0, what will happen? R becomes R. You see, as when there is no when the reaction is not yet started, what will happen? Concentration of reactants becomes initial concentration. That's why here it is becoming R is equal to R naught. Now it is becoming minus ln R naught is equal to k into 0 plus I, which implies that I is equal to minus ln R naught. Now substitute this I value. Substitute this I value in equation 1. Substitute this I value in equation 1. If I substitute, no, what will happen? Minus ln R is equal to kt Kt minus ln r. So you bring this side ln r naught minus ln r is equal to Kt. ln r naught ln r minus ln r is equal to Kt minus ln r. If I am bringing this ln r, this r naught this side, ln r naught minus, as it is a minus, which is brought to this side, it becomes positive. That's why ln r naught minus ln r is equal to Kt. Now it is in the form of ln a by b. What is the form of ln a by b? ln a minus ln b. ln a minus ln b, the basic formula in logarithms. ln ab is equal to ln a plus ln b. ln a by b is equal to ln a minus ln b. That's why it is in the form of ln a minus ln b. That's why I can write it as the ln a by b. That is, a is r naught and b is equal to Kt. Now see, k is equal to 1 by t into ln r naught minus r naught minus r. We know that log base e is equal to 2.303 log base 10. That's why ln or log both are same only. ln e or log base e. ln or log base e. ln or log base e is equal to 2.303 into log base 10. If I substitute this, then what is happening? K is equal to 2.30 by 3 into log r naught by r. You see, if I write 3, then what it means? Is it is a plus 3? No need to say plus. If it is a minus, then I have to mention this. Similarly, here also, if we are writing log, unless otherwise if it is specified, otherwise it is a 10 only, base 10 only. Right? Getting or not here? Here, if it is not specified, we can take it as a granted. It is a log base 10. Log base 10. Right? So this is the expression for rate constant of a first order reaction. Derive the equation for the rate constant of a first order reaction. This is the important question. Similarly, for zero order reaction, derive the expression for rate constant of a zero order reaction. Now this is an equation for the rate constant of a first order reaction. Now we need to derive expression for half-life of a first order reaction. Half-life of a first order reaction. Half-life of a first order reaction. Already we have seen what is the half-life. Half-life is the time required to reduce the concentration of reactants to half of its initial value. Half-life is the time required to reduce the concentration of reactants to half of its initial value. Right? So it is denoted by T half. From the previous one, what is the rate constant expression? 2.303 by T into log R naught by R. This is the expression for rate constant of a first order reaction. Now, when T is equal to T half, whatever time that is equal to half-life of that reaction, then what will happen? R becomes R naught by 2. R becomes R naught by 2. So don't confuse with R and R naught. R naught is the initial concentration. R is the concentration of reactants after time T. Suppose around after 10 minutes, what is the reaction? What is the concentration of reactants? That is R. Initially, we will take something that is R naught. So when time T is equal to half, as per the definition of half-life, R is the concentration of reactants after time T. The time is T half, becomes R naught by 2. If I substitute those values by 3 into in place of T, what T of log, what will happen? R naught by R naught by 2. R naught by 2. Now, you see here 2.303 by K. P of is equal to, just I am cross multiplied. I brought this K to this numerator denominator and T to numerator. Then it is becoming log R naught by R naught into, right? Because it is reciprocal, no? That's why R naught gets cancelled. It is becoming 2.303 by K into log 2. You see, we know that log 2 value is, log 2 base 10 value is 0.3010. That's why T half is equal to 2.303 into 0.3010 by K. So, which is becoming how much? 0.693 by K. Now, T half is equal to 0.693 by K. So, this is the expression for the rate half-life of a first order reaction. Half-life of a first order reaction. T half is equal to 0.693 by K. This is the expression for the half-life of a first order reaction. So from this expression, what we can see is there is no reactant term. See, please try to remember what is the half-life of a first order reaction. T of is equal to R naught by 2K. R naught by 2K. What is the expression for the half-life of a first order reaction? 0.693 by K. Here in zero order, there is a reactant term, concentration of reactant term. Here there is no concentration of reactant term. That's why we can say that half-life of a first order reaction is independent of the concentration of reactants. Independent of the concentration of reactants. So here also in intermediate public examination point of view, derive an expression for the first rate constant of a first order reaction, or derive an expression for the half-life of a first order reaction. So T of is equal to 0.693 by K. So this is expression for the half-life of a first order reaction. Now we need to see some plots related to the first order reaction. Graphs or plots related to first order reaction. So now we know that what is the rate constant? Rate is equal to, rate equation is equal to R power 1 where K into R. Right, here R is the concentration of reactants after time T. K is equal to what? Rate is equal to K into R power 1 where K is equal to R power 1 is, we can take it out. That's why K is equal to concentration of reactants. K into concentration of reactants. Right, here if I plot rate versus concentration of reactants, the plot is, it is in the form of y is equal to mx. That's why this is the passing through horizon. This is passing through horizon, and the slope of this plot is equal to k. Just the same plot for zero order reaction, how it appears. Just compare once here. Concentration of reactants. This is independent of parallel to the x-axis. Parallel to the x-axis. So this is the difference between zero order plot and first order plot. Zero order plot and first order plot. Now we need to see another graph related to the first order reaction. Now, what is the rate constant expression? K is equal to 2.303 by T into R naught by R. You see, it is in the form of log A by B. Now I can write, you see, KT by 2.303 is equal to log R naught minus log R. Just simply what I did, I brought T this side and 2.303 that side. Then I will log A by B, log A by N minus log B. Now just exchange the terms. If I am bringing log R this side, then what will happen? And K to this side, minus K by 2.303 into T plus log R. Log R. Now it is in the form of y is equal to mx plus c. Y is equal to mx plus c. If I plot like this, if I plot log concentration versus time plot, log concentration of reactant versus time plot. Now this is also a straight line with a negative slope and an intercept. And the slope is equal to what? Minus k by 2.303 and log r. Right? So in zero order, we have plotted concentration of reactants versus time. There also the plot is a straight line with a negative slope and positive intercept. Here the plot is between what? Log R versus time. Log concentration of reactant versus time with a negative slope is a straight line with a negative slope is corresponds to first order reactions. First order reactions. Now there is another plot that is corresponds to half-life versus. You see, with the, what we have expression we have seen 0.693 by K. I am writing it as the 0.693 by K into R naught power 0. That's why here it is becoming some other new constant R naught power 0. T. So if I plot, what will happen? The T of is independent of the concentration of reactants. That's why it is parallel to x-axis. It is parallel to x-axis. So this is these are the three plots. One is log rate versus type, which is passing through origin, which is rate versus concentration of reactants, which is passing through origin. Second one is log concentration of reactant versus type. The third one is half-life versus initial concentration of reactants. So these are the plots related to the first order reactions. Now we need to see what are the examples for the first order reactions. What are the examples for the first order reactions? One is decomposition of H2O2 in aqueous solution. One is what? Decomposition of H2O2 in aqueous solution. That is 2H2O2 with raised to 2H2O plus O2. 2H2O plus O2. This is an example for the first order reaction. Second one is decomposition of ammonium nitrate. Right? NH4NO3. NH4NO3. It is decomposed as the N2 plus 2H. Sorry, 3H. Right? So this is examples for the first order reactions. Right? So with this we have completed zero order reactions and first order reactions. Briefly in both the order reactions, common points are first we have defined the what is a zero order reaction, what is a first order reaction. Now in both the cases we have assumed a zero order reaction. In this case we have assumed a first order reaction, and then we have derived an expression for the rate constants. Then we have derived an expression for the half-life period, and then we have seen some plots. Then we have seen some examples. Right? So thank you. Now please keep watching Renault chemistry classes. In the next class, I am going to discuss about the effect of catalyst and effect of temperature. Thank you.